morning, friends. I am Dr. Dwivedhi, professor from Institute of Aeronautical Engineering, Hyderabad, India. I feel immense happiness to deliver the course named as Aircraft Stability and Control. Today, I am in lecture number 3. The topic of the lecture is stability and trim. In previous classes, I have discussed about the different types of motions, different types of stability, that is the static stability and the dynamic stability. And I have also discussed in my previous class about 6 types of motions. In that, if I see that out of 6 types of motion, there are 4 types of motion in which static stability persists, and out of these 4, there are only 2 motions, that is the damped oscillation and the subsidence. These 2 motions are dynamic stable also. So I have expressed that to have a dynamic stability, the system should be first statically stable. However, to have the static stability, it doesn't mean that it should be dynamic stable. We have discussed that if the tendency of any system after disturbance is to revert to its equilibrium position, then we can say that aircraft is statically stable. In the present unit, we are discussing about longitudinal static stability only. So we will see that today how the stability and how the trim requirement can be met. From here onwards, we are in the process of stability. Before that, it was just introduction for the different systems. In this lecture, I am going to discuss about the introduction, then approaches of aircraft performance, approaches for aircraft stability and control, effects of location of aerodynamic center with respect to center of gravity, aerodynamic coefficients, comparison of symmetrical and cambered airfoil, then last it will be trim for stable aircraft. So these topics I am going to cover and hope this will be very interesting and you all will enjoy the class. In introduction, you know that we have done in our previous semester about aircraft performance. In aircraft performance, we deal with translatory motion of the aircraft, and we have also taken as a point mass system model for approximation, and this was used. But while dealing with stability and control, the translatory motion as well as rotary motion of the aircraft is taken into consideration. So in this, rotation of the aircraft is also considered. In stability, not only the mass but mass distribution matters. So we cannot take here as a mass, as a point mass, but at different places we have the different mass system. So point mass approximation not valid for stability and control due to the moment of inertia which is persisting on the aircraft due to the rotation of the aircraft. The phases of the flight during aircraft systems, which we have taken as a takeoff, climb, descent, loiter, landing, as shown in this figure. I can see in this figure that if the aircraft is here and it start moving, this is on the runway. So this is up to here, it is called the takeoff. From here, the angle of attack is increased, nose is up. So this is called the climb. Till the point where the steady state and a constant altitude with constant speed aircraft is flying, that phase of the flight is known as a cruise. And after reaching to the destination, near the destination, aircraft start coming down, and if the runway is not clear, then aircraft will start loitering like this on the circuit of the runway, and as and when it gets the permission from air traffic controller, aircraft will be landing on the runway here and it will stop at the dispersal. So these are the phases of the flight which we have covered fully in our previous semester, the course which is aircraft performance, and that is also known as a flight mechanics. So now I want to just review something about this course and about stability and the control. So how we are going to get lift? If aircraft is flying at a constant lift where it is like this, just you can see here, it is, this is the lift, this is the weight, this is the thrust, and this is the drag. So it is a constant speed, but if you want to give some extra lift, so how we are going to give the lift? This we have not studied in our flight mechanics. Which component plays a role for generating additional lift? So in this steady state flight, which component is responsible to give additional lift? It is the control surfaces which will deflect it to and get the response. So if we want to increase the altitude, there is a tail and there is a elevator. This elevator has to put down to make this thing down, and it has to be put up if you want to make this thing nose up and nose down. So for down, your elevator has to go down, and for up, elevator has to go up. So if you want to increase the angle of attack, or if you want to differ from its steady state flight, you have to use the control. And this control will take some time to respond. So we need to build a relationship with stability and control. So you see that once I apply the control, then only stability will change. For cruise, some delta E is required. Does it come immediately or transient response? So stability with transient response is referred as a dynamic stability. Okay, so you see that we are in this unit, we are only considering the static stability, and we can see that as and when I apply the control will not immediately respond. It will take some time, transient. It will take some time, but after some time, if it is stabilizing, then we can say that aircraft is dynamically stable. So we have two types of stability, that is static stability and the dynamic stability, and further these have three types, that is positive static stability, negative static stability or instability, and the neutral static stability. Same way, dynamic stability also has the positive dynamic stability, negative dynamic instability, and neutral dynamic stability. So these can be achieved. And if you talk about the controls, we have the four here primary controls. They are the elevator, ailerons, rudder, and the canard. These are the controls which are used for aircraft operation. Okay, now I will go with some further to discuss about the stability. So every system which is in equilibrium, and then if disturbed, and if the tendency of the system is to come back to its equilibrium condition, then we say that the system is in static stable. This you can see here. I have already shown this diagram earlier also in my unit 1 and this class lecture number 1 and 2. So again here I am emphasizing that this is the case of a one bob here, and you apply some force, and this force has made to reach here. And if you remove this force from here, what is the tendency of this? Whether this trying to come to its equilibrium or not. If this bob is the tendency of this bob is to revert to its equilibrium position, then we can say that the initial tendency of this bob is to revert to its equilibrium position. So we can say that this system is statically stable. If you see the next case, if I revert this ball here and put this ball at the apex of this curvature and apply some force here and up to reach here, and you remove this force from here, if you see here, the tendency is go away and away and away. So here the tendency, if I draw the plot here for this, I have disturbed from here to here, the case 1, that is the stability, and if I leave this force, it will try to come to this position like this. This is a stable. Okay, but if I push this thing here to here and it start going like this, this is the unstable or unstable. Okay, so like this, this case, this do not come to its equilibrium position. It will go away from equilibrium is this. But in this case, the second case, case number 2, I am writing here case number 2, and this is the case number 1. So case number 1 is tendency to come to its equilibrium. Then it is a stable. And if case number 2, you are disturbed but it is going away from it, this is the unstable case. So here we can see that in this diagram that how these things are happening. This is the aircraft. In this aircraft, it is in a steady state cruise flight where the equations of motion in which the steady state L is equal to lift is equal to weight and this thrust is equal to drag is in equilibrium. But if you make one alpha disturbance due to the gust or some other thing, so if the alpha is increased, this lift will increase and it will try to go nose up. Okay, so it goes nose up, but due to increase in this lift, it will generate a moment. This will counter it. I am writing the CM1 and this will generate CM2. So CM1 will be CM2 or the net moment will be 0. So it is now equilibrium. And the tendency of this thing is to come to its equilibrium position. That is also the one issue. So in this condition, we can say that aircraft is statically stable. So we have to see the equilibrium, then give some disturbance here, delta alpha, it is shown here. If the tendency is to come to its equilibrium, then it is said to be static stable. Most of the fighter aircrafts are marginally unstable. You know that the fighter aircrafts, the purpose of the fighter aircraft is to have a very high maneuverability. If we give the high static stability, the maneuverability will be reduced. So we try to design in such a way that the aircraft is marginally unstable. Not a very high unstable, but marginally unstable so that its maneuvering will be very high and the performance of maneuvering of the fighter aircrafts will be tremendously good. So we try to make the fighter aircraft in such a way that its maneuverability will be very high. Now same thing I am explaining with the help of spring mass system, the static stability and the dynamic stability. So in the case 1 here, I have shown this is the spring and this is the mass here, and here is a vacuum, nothing is here, and if you disturb by this force, this mass will come and it will start oscillating, and it will continue oscillating. So this here and this, once you have given this lift, this spring will pull and again it will pull down. So this spring will give here static stability. So here we can say that your aircraft tail, horizontal tail, which we are putting behind the fuselage, at the end of the fuselage, this acts as a spring and this gives the stiffness, and this stiffness is trying to revert the position to its equilibrium, because it is in the vacuum, so it will continue vibrating, but the tendency is always come to its equilibrium position. So here case 1, spring mass in vacuum acts as a static stable system. Spring gives static stability. So this is for the case 1. If you take the case 2, it is same, only this blue color dot, that is some oil or some fluid is put inside this thing, and this acts like a damper. So if you see the case 1, it is continue vibrating, but here due to this media, and media is oil or something, and this media is called the damping. So after some time it will come to its equilibrium position. Okay, so this case 2 is dynamic stable. So if the system is filled with oil or water, it will act as a damper and the system will come to stand still after some time, finite time. It is a dynamic stable system as the amplitude is reducing with respect to the time. For dynamic system, this damping and stiffness is required to achieve the system stability. So we can go like this. The aim of this course is to understand the stability, then understand the control, then understand the response, how much time it is taking to come to its equilibrium, and then our aim is to understand the handling quality of the aircraft. So these are the motto of this our class or this course. So first we have to understand the stability, and once we talk about the stability, it is a static stability and the dynamic stability. Then we have to see about the effect of the control, and after that we have to see how much response or how much time it is taking to come to its equilibrium, and then how smooth aircraft is there, means how nicely aircraft is controllable. And I have shown here that if the black color is a case 1 for the static stability and the red is for the dynamic stability, in a finite time it is coming to its equilibrium position, then we can say that aircraft is dynamic stable. And if the only tendency is there, then it is a static stability. To have the dynamic stability, aircraft should have first statically stable. Now I am going to discuss very, very important relation with center of gravity and the aerodynamic center. So aerodynamic center and the center of gravity relationship. Aerodynamic center is the point where pitching moment is independent of the angle of attack. It means whatever angle of attack you give, it will not affect the pitching moment. So that point we say it is a aerodynamic center. We are now only focusing on the static stability. Here we can say the two cases can be there for the location of the AC and the CG. You see the first case here, the CG is ahead of the AC. So both are, you just assume at a symmetrical airfoil, you don't think in this. So AC will be always at C/4. Okay. So here we can see the AC is here. This is the AC and here is the CG. This one is the CG. Always your flow velocity V will act on the CG, on the AC, and initially it was at alpha star. Okay. Assume it is a 2 degree, and all of a sudden one gust came and 0.5 degree increase of angle of attack took place, and that is the delta alpha. So this delta alpha will generate a delta L force here, and this delta L into x will generate a moment, and this direction of moment will be, it is called Cm alpha. This Cm alpha is negative, nose down. So this case is case of stability. So in this, Cm alpha is negative, and we can say that this state or this condition, when the center of gravity is ahead of the aerodynamic center, the system is statically stable. If you see the next case, the CG is behind to the AC. So if you see here, this is the CG and this is the AC, and if it is the symmetrical airfoil, this AC will be always at C by 4. Okay, C by 4. So at this condition also, this lift is generated, and this lift will turn the aircraft in this. That is called Cm alpha positive. Nose will go up. So in this case, if it is so, then aircraft is statically unstable. Okay, so this is the case of statically unstable as Cm alpha is greater than 0 or the positive. So to have the static stability, we should have Cm alpha or dCm by d alpha should be less than 0, and this is called negative. If this is case, then it is a statically stable. I think it is very much clear. And so anytime if you want to assess that aircraft is statically stable or not, we have to find out Cm, dCm, the difference of coefficient of moment with difference of angle of attack, divide it, and if you are getting the negative result or the slope, then it is a statically stable case. Now, production of moment in an aircraft. This is again in the same way. Primary lifting surface is wing of the airplane. Fuselage effect we neglect normally. First case, when CG is ahead of the wing aerodynamic center, it is self-stable. If you see here, the case 1 here, I told just now, if AC is behind the CG or CG is ahead of the AC, this Cm alpha of this thing will be negative, and it is a stable case. So we don't need here any tail and all. Second case, when AC is ahead of the CG. Just you can see here, this is the second case, this is the second, this is the first, and this is the here third case. So in the second case, when aerodynamic center, this AC is ahead, and this you can write as a x bar. Always we write with respect, x bar means what? X by C. It is called x bar, where x is this distance and divided by chord length. So it will come some in percentage, or this we can write 0.1. So this is a non-dimensional number, because here we are taking the non-dimensional. So here also we should take the non-dimensional x bar. So once we write x bar, it is a non-dimensional. It will not have the unit. It means it is divided by the chord length. So in this, what happened, that if the aerodynamic center is ahead of the CG, and if any disturbance of alpha is taking place, this is the alpha, it will generate some additional lift, and this additional lift into this distance will try to make nose up. I have shown here the nose up will be there, nose up, and this nose up will make aircraft unstable. The tendency of this aircraft is not to come to its equilibrium position, so we need to have something to make nose down. That is why we have to put a horizontal tail and also one control. This control is called the elevator. So here if it is in the positive, so it will generate a lift also in the same proportionate, and this xt bar, so this x bar t is equal to x t divided by c bar. So here also this pitching moment cm into x bar t. So this cmt has to equal the cmw. So if this is the case, it is unstable, but to counter this aircraft instability and make it stable, we need one part that is called horizontal tail or the horizontal stabilizer, and this horizontal stabilizer will try to counter the cmw, which is generated, the coefficient of movement generated by the wing. Now if you see, the third case is adding a surface ahead of the wing called the canard. So if we add a canard ahead of this wing, so if you see here, it is, if AC is behind the CG, AC is behind the CG, so it is making nose down, but if you put this canard, it will make nose up. So in this case, your canard is also can be used as a horizontal stabilizer to stabilize the aircraft. Any flying surface ahead of the center of gravity will give destabilizing effect, and behind it gives the stabilizing effect. So this is the conclusion of that. If you want a stabilizing your aerodynamic surfaces like wing, horizontal tail, if it is behind the CG, this will give the stabilizing, and if it is ahead of the CG, it will give destabilizing effect. So this we have to take care, and we have to understand that the location of center of gravity, location of aerodynamic center, and also location of horizontal stabilizer, it may be tail or it may be the fore, and like a canard or the horizontal tail, we should consider for our design as per the need of or the performance or the stability requirement of the aircraft. So we can now discuss about the aerodynamic coefficients. So this we can see that the coefficient of lift, first thing is lift is equal to half rho v square s cl, where cl is lift coefficient. So we take all things in a non-dimensional form. Just now I told for the distance also we have to take in. So if you want a coefficient of lift, CL is equal to lift divided by half rho v square s, where s is surface area, v infinity is free stream velocity, rho is density of air, L is equal to lift produced. Okay, so this is the coefficient of lift. Now if you want to see the coefficient of drag, so we know that drag is equal to D is equal to half rho v square infinity s cd, where cd is the coefficient of drag, cd is equal to drag d divided by half rho v square infinity s. Okay, so in this way we can find out the drag. Same way for the pitching moment coefficient. So we know that pitching moment is equal to half rho v square s c bar into cm, where cm is the pitching moment. So cm is equal to pitching moment divided by half rho v square s c bar. So these are the three aerodynamic coefficients. So this you have to understand, and you should know that these things will be used for our further discussion. So now if we discuss about comparison of symmetrical and the cambered airfoil, so this we can see here that how we can compare. So if you take the symmetrical airfoil, okay, just I will write here. I am drawing the symmetrical airfoil. May not be exactly okay, but symmetrical means both sides it should be equal. Okay, so that is the symmetrical airfoil, and very important in this, in symmetrical airfoil, aerodynamic center is at, if this is the chord length, this is the chord, it is expressed as small c. So your aerodynamic center AC will be at c by 4. So that is the specialty of symmetrical airfoil. And in this symmetrical airfoil, a very good, at alpha, that is called angle of attack, at alpha, angle of attack is equal to 0. The lift coefficient will be 0. Okay, so if you draw the plot for CL versus alpha, 0, it will go like this. Okay, and this is the highest. This is called the stall. This is called the stall angle of attack or stall angle. We should not operate in this range at all. Okay, so in this, at 0 angle of attack, you will get 0 lift, and you will have CL is equal to 0 and also CM is equal to 0. No pitching moment, because the pitching moment is lift into X, but lift is 0. It means there is no pitching moment in the symmetrical airfoil at 0 angle of attack. Now if I draw a cambered airfoil, this is the cambered airfoil. So at alpha is equal to 0, lift is not is equal to 0. Some value, and if you draw the plot of a cambered airfoil, a positive lift will be there. So this is the CL and this is the alpha. At 0 angle of attack, it will do like this and it will come like this. Okay, so this is the stall point here, and this is the CL naught. Means at alpha is equal to 0, you will have some positive value of lift, and at some minus alpha, this is called the trim point. Okay, so your cambered airfoil, the trim point means at the point where you don't have the lift, that is called the trim point. And in this case, this is a minus alpha, and in this case your CL will be 0 and CM will be 0. So that is the difference. So if you draw the this thing, CM versus alpha for the this cambered airfoil, for this it will come like this. This is for the symmetric, and for cambered one It is like this. Okay, so this is the difference between the symmetrical and camber airfoil for the coefficient of lift and the pitching moment. I think it will be very much clear to understand, because this concept will be used for the further expression. Now I am going to discuss about the trim case, and in this trim case you can see that how we can get the trim. If you see what is the difference between the this stability and the performance. Okay, so in our performance case we have not gone some special points like this. You can say first thing is aerodynamic center. Aerodynamic center. We have not discussed in our aerodynamic performance course much about the aerodynamic center and how the moment variation about a point called CG is taking place due to variation of the aerodynamic forces. Third case is very important and it is very new for this course, and this we will be understanding very well. Coefficient of moment AC of the wing. This we have not considered before. So this we have to understand that what is this CMAC. Okay, so this we have to see that aerodynamic center I have already explained you just now, and how the moment variation about a point CG, these also we have taken, and now I will concentrate on CMAC and how this coefficient of moment is this AC is changed. First I will take the case 1, symmetrical. Okay, symmetrical airfoil. In this symmetrical airfoil, if we see this, the variation of the pressure distribution, it will go like this, and at 0 it will go like this. Both will act at the same point and same amount. So this is the F1 and this is the F2. So F1 minus F2 is equal to 0. And they all will act at C by 4. This is the C by 4 and this is the aerodynamic center at alpha is equal to 0. But if you see about the case 2 for the cambered airfoil. So in this case, we can see here that for the cambered airfoil, if I make like this, so in this F1 upper side will be here and F2 will be in this, and a net force, this is here the AC. So if you see here again, I am making, if I want to make this representation in one point, so this is called the aerodynamic center and this is the lift, this is the drag, and there will be a moment that is called CMAC wing. So this CMAC wing is very important, and that we have to, the value of this CMAC wing ranges from minus 0.01 to minus 0.1. So this value we have to understand that CMAC, coefficient of moment. So here you know this, the force of this F1 and F2 will generate a moment, this and this. So if we take here, this we will make as AC, and this moment we will transfer in a new position here, and this CMAC is inherent in the cambered airfoil at 0 angle of attack also it will be there, and the value of this CMAC will be 0.01 to 0.1. Okay, so now we will see that how this thing, assume that the CG is ahead of the AC. In first case, okay, this we will see that the case 1, the CG is ahead of C by 4. Okay, so this is the case, and so we will see that it is statically stable or not. Statically stable or not. So that is the question. So if I make this like this, here is the CG, this is the AC. So in this AC, you will get the delta lift, and here you will get the drag. So there will be a CMAC wing. Okay, so here if you see, the CM has here, the CM has initial tendency to come to initial equilibrium. Okay, so here if you see, this force will act like this. So CM alpha is negative. So CM alpha is negative, and so it is a static stable. Now case 2, if I see here, I will make the CG is behind. This is CG, this is the AC. So here this is the lift, and it will try to move, and there is a CM AC. Okay, so here it will try to make aircraft nose up. You see, this is making nose up. So this case is unstable. Okay, this case is unstable, and this we can see here further in our trim and stable, that if I draw, I have already drawn the plot like this. Trim, I want to discuss about the trim for symmetrical airfoil. Symmetrical wing. If it is a symmetrical wing, then what will happen? For the symmetrical, we have discussed that at alpha is equal to 0, this is the case 1. Okay, so this is alpha, this point is alpha, and this is the CM. Okay, and this is for the symmetrical. Okay, this is the case 1 and case 2. So if I see here that if CG is ahead, CG and AC, if the CG is ahead, this will try to move in this. So it is a stable case. Okay, so it is a stable. Another case, if you see for the cambered airfoil, for the cambered wing, what will happen? If it is a cambered wing, just I will show here, and this is the cambered wing, here is the CG, and this is the AC, this will be a lift, this will be the drag, and there will be a CMAC, but this CMAC is always negative. Okay, it is shown here positive, but it is always negative. So this will try to make. At alpha is equal to 0 also, there will be the some value of Cm here. So this is the point where at alpha is equal to 0, some negative Cm is persisting. But if we take like this, it will intercept somewhere here. This is the trim point. Means in this case, alpha is equal to 0. It is a trim for symmetric. But here alpha is equal to some minus value. At minus value, this will work. Okay, so at minus value, it will work, and you will see that there is a alpha is equal to. So this you can see here that for the cambered airfoil, it is at minus some alpha, maybe minus 4 degree, you are getting the trim condition. But like this we don't want. If it is like this, it is not good. It is not good to have like this, because we want a positive trim angle of attack. So your actual trim should be like this. Means this is your trim angle of attack, and it should be a positive. So it will come when you have Cm naught. This is called Cm versus alpha. That Cm naught should be greater than 0. So first condition for any aircraft stability, to have Cm naught greater than 0 and Cm alpha less than 0 means negative, and this should be positive. So here at alpha is equal to 0 means the coefficient of moment at alpha is equal to 0, you should have Cm naught greater than 0. If it is like this, then your conditions are achieved. Okay, so in this way we can say that your Cm naught is greater than 0, and we can get the static stability of the aircraft. So for the cambered airfoil, for the cambered wing, at alpha is equal to 0, we will have minus CL naught into X bar. This is, you see here, what is this? This is the Cm, and this is the, if I draw here CL versus alpha, so this is CL naught. Okay, so this CL naught into this X, this is the X bar. So this is the moment in this direction, so it is minus, plus this Cm alpha, Cm AC of the wing. This is the total moment of the at 0 angle of attack. At alpha is equal to 0, this you will get the moment. So at Cm alpha 0, it will generate a large negative moment. Okay, so in this way we need to get a trim point, and the slope of this thing should be positive. So in this case you will have lift is equal to weight and thrust is equal to drag in this steady state, and in this condition you need some alpha, and this should be always positive. So this is called the trim point, and aircraft has to be trimmed before it is flown for the aircraft. So we try to make that here 2 points are considered for aircraft longitudinal static stability. First case, Cm alpha should be less than 0 and Cm naught should be greater than 0, and this Cm naught is required. Why? because we want at a positive trim. Positive trim. So your intercept of this slope, and this slope should be negative, means from high value to low value it should go. If the plot is the plot of Cm versus alpha or Cm versus Cl, both are in the negative direction, it means dCm by d alpha is less than 0. It should be less than 0 or negative, and the intercept Cm naught should be greater than 0. If you are able to do this, you can say that aircraft is statically stable. So in this way, I understand that I have covered the topic today. Some important topics I have already covered, and I can see that these are the topics: introduction and approaches for aircraft performance, approaches for aircraft stability and control, effect of location of aerodynamic center with respect to the center of gravity, aerodynamic coefficients, comparison of symmetrical and cambered airfoil, and trim of the stable aircraft. This I have covered. I think I should again emphasize that the trim is very important, and this trim should have at positive angle of attack. If trim is not happening at the positive angle of attack, the aircraft flying is not possible. To fly the aircraft should have a positive angle of attack where your steady state can be achieved. The lift should be equal to weight, and the thrust should be equal to the drag. If these conditions are met, we can say that aircraft is statically stable. So if we want to design the aircraft, we must make sure that aircraft should be statically stable. Once we talk about aircraft statically stable, in this unit I am talking only longitudinal static stable. If I am missing somewhere longitudinal, you understand that I am talking only longitudinal, means pitching. The longitudinal which happen with respect to the y-axis or the lateral axis of the aircraft. In pitching motion, the nose goes up and down. If you see here, I am talking about the longitudinal, means this axis will remain constant and it will pitch up and down like this. So in this case, we should make sure that the tendency of the nose should come down. It should not go up if angle of attack is increased. So on increase of angle of attack, nose should go down, not up. If the tendency is like this, aircraft is longitudinal statically stable. But only this condition will not solve the problem, because we want to fly the aircraft also, and flying is only possible with a positive angle of attack. So the trim condition should also fall at Cm naught is equal to greater than 0. So we can see here that for this trim, we should have Cm naught greater than 0. If I draw here one plot again, Cm versus alpha, here it should intersect at positive Cm. This is called the Cm naught, and Cm naught value, and this is called the trim. So if this value is 0.6 Cl and the slope of this thing is 0.1 Cm alpha, so this value will be how much? This into this, it will be 0.06. So your Cm naught should be 0.06. So if you know that at what coefficient of lift you are going to trim, and you know this angle and you know this slope, you can find out this Cm naught value, and by this you can design your tail, horizontal tail or the canard in such a way that you get the value of Cm naught. Okay, so in this I have my references are this Yachout, aircraft flight mechanics, and this aircraft stability and control by R.C. Nelson. Any questions you are welcome to ask. Thank you very much for joining, and I will be continuing my next lecture also. Please do tune with this. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.